First of all, I would like to thank you because, as you might know, the temperature might be very high in Europe. So thank you for organizing the curricula in a cool country. Okay, so here are some of the points I will talk about. I will not talk about the grey one, so just one word about this one. We are trying to use Seagull, which is an SFD code, as several modules, one for the star function rate, another one for the depth, etc. And I'm working with mathematicians to replace each module with some deep learning stuff, so that will be very fast, because we need to build the practice sample, and Seagull is fast, but not enough for this stuff, so we are trying to replace each module by deep learning. Okay, then we'll have PDR models soon, and dust and chemical emission models. So first things, Galex Herschel match catalog. So we published a paper in January this year. The data are available. We did some cross-matching between UV and far infrared. It was not always easy, but working with my former student Firas and with Nagisa, we were able to match this, and we started to follow up by looking at some of the interesting targets with the NOEMA, which is an interferometer in millimeter, and to identify some very high redshift sources. So this is published and the data is available. Next one, which is more important right now because it's on new data, and there is some new CFHT WIRCAM data that will be available, or actually is available now. So we have some data submitted, and we had several fields here, 11 in Canada, 11 in France, and 7 in China. So, well, it was on A, B, and C, but everything seems to have been observed now. And we now have 8 fields rated C observed, 4 in A, 4 in China, and 4 in Canada. So that means that we more or less cover almost everything we have here, which is quite nice. So the data is now available, and if you look at this, that's the email from CFHT, so Marcin Sawicki in Canada and Fanting Yuan in China. So that will be available for 12 months, but well, everyone can access the data if TRL is public. So that's something we need to discuss, how to process this data. We don't have the people to work on this in France. So, and well, apparently in China and Canada as well. So that's something that is interesting because we will need to do that. Second one, this is I1 30-meter telescope. I went there, so it was quite nice in winter. I was there in February, and we had some observation. So the good things is that we got the first Nikatu data taken in the NEP. That's this program, Picnic in the NEP. The bad point is that 2 fields only were observed. We had 5 or 6, I don't remember. But well, we will resubmit this later in September. And this field should get us about 170 square arc minutes down to at 2 mm, about 0.5 millilatency. So that's quite deep. That's a pilot program. And Nikatu seems to work well. The pipeline is still proprietary to the NECA team, but I'm part of it, so someone is running the pipeline for me. We'll get this first field analyzed and resubmit in September to get this. And well, if this pilot project is successful, then we might get on a large program to cover with this level of sensitivity, maybe the NEP deep, so 0.5 square degree. That's well, quite a large amount of time, something like 200 or 300 hours, but well, it's possible. For this program, I asked 35 hours and it was accepted. So maybe if it is accepted next time, we can move to the next level. So we'll have this data, and from that, of course, we'll have some millimeter data at 1 and 2 millimeter, quite deep. We need to define the strategy. Next one is the NEPL project, for those who don't remember. That's one object detected in the NEP field with Herschel. very red. We had some additional data from CSA. Now we have other things as well. And it appeared to be a source which is, you see the redshift, photometric redshift range in agreement with this. Well, of course, it's not very well constrained because we have only 4 modes. It's not detected here. And you have the data right here from Galex to Herschel. This is the Subaru data that Nagisa sent. So we had several objects around with several photometric redshifts. This is the lens, massive galaxy at redshift 0.8. And then we were trying to see if in these maps we can see the lensed galaxy. Actually, we don't. And so we get some, so Gemini was the optical spectrum. We observe this source with NOEMAS, that's the antenna, the former Plateau de Bure. So we detected the continuum, it's here. It's approximately in the center, so very close to the lens. And we have one big line, which is here. So same thing, the good point is that one line is detected, but one line is detected only, so we don't know the redshift. We will finish to process all the data at 1 2mm, try to see if there is, because I only process half of the data, all the wavelength range, but half of the data. So maybe there is another fainter line that I didn't see yet. And I'm planning to resubmit the proposal to see if there is another one. Right now, we have ruled out that it's Galaxy at redshift 7 or 6-ish, but we still have 2 options, 360 or 4.8 for the redshift. This is consistent with the fact that we have one line only. This object is not detected at all in optical, so we tried before with Gemini, and so we have 2 options yet. So we need to confirm which one of the 2 it is. Well, or maybe a surprise, but we'll see.
Well, you're sure it's not lens galaxy?
We're sure it's a lens galaxy. Because
no, I mean the redshift 0.8.
Oh, this one, yeah. That's the spectrum we get. So we have identified all the absorption line.
Yeah, but the emission, radio emission.
Oh, it's not possible. That's something like an elliptical. It doesn't produce any dust like this in infrared.
Okay, okay, but there is no any line corresponding to that redshift, right?
Oh, no.
Okay.
No. Not here, at least. What we get for the elliptical here and for the oops, sorry. And for the lens is completely disconnected. We have the Akari, Spitzer, and Subaru data on the elliptical, and this and Herschel on the infrared. Okay, so well, we'll see. We need to observe it again. That's the only way. So now some news about Seagull. So Seagull, as you know, is working from far UV to the far infrared, or a little bit in radio. And now we have a student who is working to develop an X-ray module. So the basis of this is that you have the black hole here, the accretion disk, and there is some type of scope that we can use, which is alpha optical X-ray between the thin disk emission and the corona. And this is correlating to the UV luminosity for IGN. So you have here this index alpha X, and this is a 2500 angstrom luminosity, so there is a good correlation, or for type 1 QSOs at least. And so we use that. So far, no redshift evolution has been found for this relation. And so we have developed an X-Seagull, which is now working. This is a test, someone is in line. You see here 2 examples. So this is one galaxy without the X-ray. The probability luminosity has been estimated would be log L 45.5, and with the X-ray 43.5. So that means that without we overestimate the luminosity of the AGN. Well, in addition to that, the shape is different, as you can see. But the residual is quite good over X-ray to far infrared. So this X-ray module is based on some alpha wax stuff. The student is Penn State University, Guan Yang, and well, he's is in lab right now until mid-July, and he started to make the test of his X-ray module on some data. So SDSS, Cosmos, and I told him to start with Zachary as well because it's quite interesting. And you see here the luminosity that he gets. So this one is SDSS is quite bright, and the luminosity is picked on 0, I mean with and without X-ray. There is something here that is very strange. In Cosmos, the sample is at a larger redshift, 1, 2, but the data are not very dense in the near and mid-infrared, so you can see that you have quite a large dispersion. On the other hand, with Akari NEP, we have the Akari data, and of course that constrains quite nicely the agent luminosity, and it's focused around 0. I mean, that's the difference between with X-ray and without X-ray. So this seems to work quite well right now, and there is a paper right now being written and will be submitted probably at the end of the summer. So we will make this module public, of course, and people can use it.
Can you just explain the Cosmos plot again?
Oh, sorry.
It looks like there's a complete explosion of points. So what does that mean?
Well, it means that without X-ray, you badly estimate AGN luminosity. Well, it seems to be quite structural. I'm not sure why, but you missed a lot of AGN luminosity.
Well, it's because you're missing the mid-infrared that you have in NEP.
Well, yes, probably. This one is, we don't have mid-infrared here, but it's very bright. I don't have the luminosity, but that's 20-ish or 22, something. But here, I will check. Is it? Well, I think that's Cosmos 1. Well, with Akari, you have a very high density of points, so you can constrain very well. You can constrain very well the AGN luminosity, and well, you can see here directly in these plots, the dispersion is quite low. So Akari is quite nice, but Akari is not everywhere, so X-ray is useful as well. And if you have Akari and X-ray, well, it's even better. Okay, so that was technical news. Now some scientific news. The first one is some work that I'm doing with Hiro, one postdoc from Banani, and Patrice Tonnet, who is a chemist, and he came to lab. So we work on the understanding the dust formation and destruction in low metallicity galaxies at redshift 0, but also at very high redshift, 4 to 10. So what we try to do is to understand this type of galaxy. This is what by Kabak et al. That's a sample of Lionel galaxy at redshift 5-ish approximately. That's the UV slot beta and the IRX value, and they found that some objects are too low with respect to what is expected. This is the Maurer law here, and even the SMC. And on the other hand, they are quite red in terms of beta, which means that this seems to indicate that there is some dust, or you have all the stars, and this seems to indicate that you have no dust. So there has been some explanation. Ferrer et al. Tried to use the fact that some stars are in stacked molecular gas. Faced et al. Invoked some special offset between dust and young stars, so that's some explanations. And what we did is to use a sample of detected Lyman-Wave galaxies between redshift 4 and 9.1 actually. And because they are covering a wide redshift range, we built an SED by using the redshift. And you use that as a template to fit the SED in infrared when you have only 1 point or even upper limits. So this is quite complex. So you have in red the LBJs, redshift 4 to 10, and includes a dwarf galaxy sample which is local. And what we do here in this diagram, you have here the specific star formation rate, SFR divided by M star, and the specific dust mass here, dust mass divided by M star. And we put a lot of models built by my postdoc with Hiro here, with different assumptions, the IMF, the no growth ASM or gross ASM, etc. A lot of physical models. And what you find here is that you have some dust formation up to this point approximately, so we don't constrain it a lot. And then dust destruction by supernovae. And well, this is the first time we see that in this redshift range. And also, this is what Asano et al. Assumed, so you see it's not in agreement. This might work for more bigger galaxies, but not for these objects. And we estimate when you have here the age of the stellar population, that's the LBG at high redshift, and the dwarf galaxies don't have the same destruction rate. So this is quite new, and we are working on the models now, but the heavy one are currently out. So we are constructing constraint for the first time, the very first phase of dust formation and destruction. It seems that it's mainly due to the supernova blast. A top IMF is preferred. That's this is Chabouillet. This is